Good morning, everyone. I'm Mason and Alaron, and I'm a part of Ozen Engineering. I'm going to have an introduction about ANSYS FLUENT or FPU 2020 R2 and the updates to that. Okay, just to give an introduction, we are Ozen Engineering. We do a lot of simulations. We are the elite channel partner of ANSYS, and we do a lot of multiphase, computational fluid dynamics, high frequency and low frequency electromagnetic problems. We sell a lot of ANSYS products from the 3D design, which is discovery or space claim, to structures, to optics, to fluids, to electronics, or even some in semiconductors. And on top of that, even embedded software such as SCADE and also system analysis such as Twin Builder, etc., and also Medini. So whatever you're working on, probably you have a tool that we can help you to get your task faster and with higher quality. So let us know, and we'll tell you what is the right tool for you. This is the information about us, and I'll go ahead and jump into the main part. And this is a little about myself. I have a PhD in fluid mechanics from Michigan State, and before that from Sharif University, and I have 10 years plus experience in fluid dynamics from writing codes and different tools, ANSYS, etc., and also a lot of automotive and some semiconductor experience in the recent job too, and mostly on thermal management, HVAC, thermodynamics, and battery modeling, turbulence, and etc. I'll be very happy to teach you guys this course about the updates of 2020 R2 and comparison with the previous versions. The first thing which is very important is the meshing workflow. Recently, we have been trying to automate the process using the journals. So there have been a lot of efforts on the meshing workflow. One of the things is using the wildcard. As you see, when you use wildcards, you can use asterisks, and then, for example, you want to have any region that has the part IN in it. So you can say IN and then asterisk before or after, and then based on that, you'll be able to search through that. And the nice thing about this wildcard is that it would be available and preserved in journal commands. So when you're going to automate the process, it will be carried over. So you can do the same operation by using the same command line. That's the main point of it. And after that, we'll go through the other update. The other update is that it can support the local sizing on edges, especially the labeled edges on mostly space claim. When you create an edge and you put a name on it, then in the new version, you would be able to put sizing on the edges. This could be done in watertight meshing or even fault tolerant. As you see here in the flange, we have an edge, we put some sizing on it, and after that, we can make that much smaller into the specific edge, which is one of the capabilities of the 2020 R2. The other thing which has been added to watertight method is support of regions, specific sizing. As you see, if you have different regions, you would be able to put different sizing constraints on it. This can be done quite easily and was not available in the previous versions. One more thing which was also added to watertight meshing, which is quite convenient, is using the imported geometry. Let's say you have a surface mesh which could be a wrapped surface, or you have an old case file which has just a surface mesh in it, but you do not have access to the detailed geometry. And you can start from there. You can now import it directly into the watertight meshing console, and then after that, you can grow volume mesh from the existing surface mesh, or you can either tweak it, improve it, and after that, create the better volume mesh out of it. So you don't need to have the actual CAD. You can start from a surface mesh, which is very helpful, especially in many examples that it's hard to get the detailed geometry. The other thing which is added to the fault-tolerant meshing is the hexacore and polyhexacore, which were two very interesting meshing options, now are available in solids as well. So you can mesh solids using these two new methods. As you see, one of the hot topics in today's industry is the electrification, and we saw that there's a lot of interest in battery modeling or in general electronic modeling, so we put a lot of effort in it. And ANSYS 2020 R2 has a more comprehensive and strong package for modeling the battery and battery packs. There were already several methods which could be used by using modules which can be added to the ANSYS platform into the FLUENT, and it can model battery in different methods. One is a CHT, which is a conjugate heat transfer, which means that you just simply put a fixed heat dissipation into the battery cells, and then you do a conjugate heat transfer to see how the temperature would be. The more advanced one is the FMU CHT. FMU is a functional mock-up that it could be done in ANSYS tools. Let's say you have a twin builder, you create an FMU out of it, or for example, you have a MATLAB code or any other, even non-ANSYS tools are also supported. You have a model for your battery cells, or you have done it already, so you can create an FMU out of it, and then that FMU can tell you that in different operating conditions, how much would be the heat generation inside the battery cells, and you put that as a fixed value inside the battery cells, and you'll do a simple conjugate heat transfer. This is very helpful because most companies already have models. They don't want to start building everything from scratch, and FMU gives them that capability. The other method is a circuit network that you represent the battery cells with electrical circuit, and based on different working conditions, different discharge rate, all those, it can tell you how much flow would go through it and how much heat generation would happen. You can use that as an input, and after that you can do the rest, which is heat transfer and conjugate heat transfer inside FLUENT and predict the temperatures inside the pack. These are all uniform heat distribution models that assume that the heat distribution is quite uniform and constant in the whole cell. And the last model, which is the most comprehensive, is the multi-scale, multi-domain, or MSMD, which actually solves for the heat dissipation inside the battery cells. It solves two equations, and it's not uniform. It can tell you what is exactly the distribution, the potential, or the heat generation in different locations of the cell. As you see, if you open the battery model in FLUENT, you have all these options. You guys have my cursor. You can see CHT, you can see FMU CHT, you can do circuit network, and then MSMD. And all these have different options also that you can put the coefficients for them to take care of the behavior of the battery. FMU, also as I mentioned, it's a functional mock-up model that could be coupled to the conjugate heat transfer. It's very convenient to use it because it does not need to be even from an ANSYS tools. You can create it in something like Twin Builder, MATLAB, or anything else, and it can just tell you, it could be something like a response surface, and it can just tell you what is the heat generation in different working conditions. And then you set up some coefficients, and you'll be set to, as you see here, you can browse it here, create the file, import the file that has that .fmu format that a lot of tools can generate that, and then you'll be good to go. The other factor which has been added specifically to this version is the battery life, which takes care of the effect of battery life and the capacity fate. The life of the battery is affected by two factors, the long-term factors and also the short-term factors. Long-term factors are mostly, I would say, the calendar life or the number of cycles it goes through. As you see here, the more number of cycles you use the battery, the capacity goes further down. So after, let's say, 10,000, you can't get the same amount of capacity that you had at 5,000 because the total capacity goes down and you can get less juice out of the battery. And of course, at lower temperature, you will get a better capacity as well. So at hot ambient or hot temperatures, it will be less juice that can be taken from the battery. And this is the equation that they use for it. And it has some constant and some coefficients in it that you should put in the model. And other than that, there's some long-term battery life factors, as you see here. When you go to the NTGK model, you can select this tab, which marks calendar life input parameters. And the parameters that I showed you in the previous slide, you can put those coefficients inside. It could be taken from test data or all the available data you have for your pack. And based on that, you can also the capacity fade table, which is also the coefficients that tells you how it fades because of temperature and the number of cycles. And these two factors would be taken care inside your model. So the battery ages and fades and the capacity goes down as you gradually use it more and more. This is the capacity fade, which is a more short-term effect. As I mentioned, when you go to higher discharge or C rate and also temperatures, the amount of juice you can get out of the battery changes. As you see at 5 discharge rates, which is shown on the right side with green and magenta curves, you can last for a longer time compared to when you have a lower discharge rate, which kind of makes sense. It's quite intuitive. And these could be put as available test data or coefficient that you have based on your experimental data or the data you get from your supplier that makes your cells. We check the capacity fade. You can import a table, as you see here, the different temperatures and different C rates, how it would change, and it would be taken care in your model. The other thing is that in the typical previous versions of NTGK model, there were assuming linear relationship between the current and the voltage. But if you look more in depth into the test data for different batteries, you can see it also depends on the discharge and temperature. So those two now could be, those two raw data could be directly imported into the NTGK model, as you see here. You can just import, you push this button that says import raw data and put those values there, and it internally automatically would interpolate and put those accurate interpolation functions inside the model for you. These are all the options that let you model the battery as close as to the test data that you have. So you have a model, you fine tune it to get all those imports, coefficients, and test data, and you get something which is very close to what you would see in the test. That's the whole point of it. The other thing is that because the battery pack was like an add-on, so you had a lot of problem in post-processing and seeing the results. So you had to define a lot of user-defined scalars. But now these, when you go to the post-processor, these have been incorporated as a native integrated field quantities. If you check battery variables, all of these are available. You can just simply select, which would save you a lot of time. The other updates that we have is mostly in the multiphase and also DPM, which is for particulate flow. In multiphase, we have different regimes. We have bubble flows, which is more volume fraction changes. We have slug flow, we have churn flow, and we have the annular flow. And these, as you see in the picture, they're quite different. Sometimes it's just volume fraction changes. Sometimes you have big chunks of fluid in it and you need to capture the interface, which is complicated. and mostly transition between these different regimes is quite tough to challenge. So a new method has been added to FLUENT multiphase, which is called generalized two-phase flow, or GenTop, which can capture all these phenomena in one shot. In other words, it can transition from one model to the other. So as you see on the left side, you have small bubbles and the volume fraction changes. Or if you go to the right side, which you have big chunks of fluid, it can capture both of it, and it's like a hybrid model that goes from one approach to the other and can capture all in one, which makes things much easier and saves you a lot of time. Here we have two examples using the new method. On the left side, we have the GenTop phase volume fraction. As you see, you have the volume fraction, but still you have big chunks of air in it. And then on the right side, again, you have GenTop results compared to the dispersed model phase results, which is the gray contours. You see it captures those big chunks of fluid as well. So it can do both small bubbles or big chunks at the same time in one shot, which is quite helpful. The other method which has been added is the subgrid scale modeling approach for specifically gas solid flows. The method we had was the homogeneous dragging model, which had some challenges. It wasn't holding that good with some test data. But in the current version, we have two new models named the filtered model and also the EMMS model, which gives you much better accuracy. Here we have a test problem, which is a challenging problem called NETL. The dotted line is the level of solid in the test, and then the left side is the homogeneous drag model, which was available in 2020 R1 and before. And these two, the EMMS and filtered model, are the new two methods which have been added to the current release. As you see, the left one was quite off compared to test, but the new ones are much, much better and you can predict it properly. So if you're dealing with fluidized beds or gas solid flows, this is going to be a big help for you. And here is another comparison. As you see, a test versus filtered versus EMMS model, that they're pretty close. It's a little overestimated by EMMS, but it's quite close to the test data. There have been some improvements in the volume of fluid method as well, such as generalized variant body force weighted method, which has been improved. And the hybrid meta also has been improved to be more stable. And the turbulence damping also have been added to the K epsilon model. We have different methods for multi-phase flows, Presto and BFW, which stands for body force weights. The Presto was quite accurate, but it was sensitive and not robust, especially with meta, so it wasn't that popular. But body force weighted was more popular because it was quite good with different measures. But the problem was that in case of very viscous flows, such as molten glass, etc., it was having poor convergence issues. So in the new version, we can improve the accuracy by one-line command, as shown here, which can be added to the TOI. And based on that, you can get very good results for BFW methods. As you see here, this was the Presto, which was the available method, but it had some issues. The old BFW, it had a lot of spikes in it, which is not physical, and you see that green area here. This is more error, and that's not correct. We need to fix it. In the new version, 2020 R2, after those modifications, you see the results. They got rid of the green region, and also the interfaces are quite clear, and there's no non-physical numerical oscillations in the parameters either, as you see here. So it has been improved significantly. The last thing, which is that the DPM has been improved. If you have a spray or injector and you have a lot of particles that's getting out of it, especially liquid, they break down into smaller droplets. And this model was included inside CFX, although FLUENT did not have it. So in this new version, we added this Chanel method into the FLUENT as well, so it can take care of the droplet breakup. And other than what I mentioned about FLUENT, there are some improvement in different physics and models too that I'll go through. If you guys have any questions, please let me know. One thing is that the impedance boundary condition has been improved in the new version. In the previous versions, you had to put an input of real complex poles that describe the frequency response. This is mostly used when you do aeroacoustic simulation. This needed a little manual work and calculating it, which was quite tough and time consuming. Now it has been done, now it's being done internally inside the tool. So if you just have the experimental acoustic material data for your surfaces, you can feed it into FLUENT and it calculates those coefficients for the poles for you, I would say, internally and directly in a shorter time. The other thing which has been taken care is the heat transfer coefficients based on the Y plus value. As you know, when you want to have convection on a surface, it's mostly being calculated by the first boundary layer or prism layer. And as your prism layer changes on different locations on a surface, then it will be sensitive to that. So to improve that, we tried to, instead of just calculating the results on the first layer, on the boundary layer, you go all the way up to the edge of the boundary layer, which would be roughly the Y plus of 300. And based on the temperature and velocity at Y plus of 300, you will be able to calculate the convective heat transfer coefficients. This is the default, which has been modified in a new version, and 300 is put there. But if you're not interested, you can modify it. But that's a good first assumption. And the results are not sensitive to the mesh, which is the most important thing and the point of this modification. The other thing is that Granta, which had almost 700 plus solid materials, now it's accessible through FLUENT. And the last but not the least is that the STL format can be exported from the results. Let's say you have ISO surfaces which have a very complicated shape, and you can export it as an XTL and as an STL format and use it in mechanical or any other tool that you're interested in. And also there's one more thing that the overset mesh has been improved. So the connectivity has been improved by adding the better adaptive mechanism. This could be done by using a one-line command that we can put in the TUI, as you see here. And that was, I think, the last thing about FLUENT. The other area that we had good amounts of expression on, a good amount of improvement on, was the expressions. Expressions is like the formula that you put inside your model, and you need to make it as user-friendly and as easy as possible. For example, imagine you want to do a multi-phase analysis, and you need to define the initial condition, that what is the level of liquid, what is the level of gas, from, let's say, this line below is liquid, from this line above is gas. So now it can be implemented in very simple, even one-line formulas and expressions, as you see here. If you have the volume fraction, say if y less than 0, then it's 1. If not, it's 0. So it's like an if command that can be just written in one line. The other thing is that a lot of properties, such as density, viscosity, conductivity, and coefficients can be put as a function of pressure, temperature, viscosity, etc. This is very interesting. For example, properties can be put as a function of either pressure or temperature, but not both of it. It's not the thermodynamic table, but it's a step forward, so it can have temperature-dependent variables. And on top of that, when you put an expression, you would be able to visualize it. As you put an expression here, you can see how it looks like as a function of independent variables. So you can predict the behavior. On top of that, there is a lot more functions that have been added to expressions. For example, sum or Bessel or step or new expression for power, which makes it much easier to use and more comprehensive. And similar to CFX, when you go to FLUENT to define an expression, especially when you want to put, for example, a species, when you put the first couple of letters, drop-down window comes up and gives you all the possible options you can put there. So it automatically searches that for you, which makes it much easier and user-friendly. And one more thing which has been requested by a lot of customers is to be able to plot the material properties as a function of, for example, temperature or pressure. And now it can be done easily in the same window, similar to expression. You can put properties and see how they behave at different operating conditions. On top of that, there have been some improvement on the graphical part of FLUENT too. One thing is that the mouse manipulation has been changed slightly because FLUENT, Space Claim, and Mechanical, they're different tools and they have different operations. For example, one was being selected by the right mouse button, the other with the left mouse button, and then we tried to make it as it was because the users were comfortable with that. But now that they're all under the umbrella of ANSYS, we try to make things more consistent. So for all of them, left mouse button would be for click for selecting the surface. It doesn't matter if it's mechanical, Space Claim, or FLUENT. And to do that, we had to make some minor changes. Specifically, they selected FLUENT now. So it's a little different from what it was. I would say maybe 10–15%. Maybe it takes a couple of days to get used to it. But the good thing is that now it's consistent between all the ANSYS tools. When you switch from Space Claim or mechanical for meshing and go to FLUENT, you don't need to get used to a new one. But on the side, keep in mind, if you don't like it, you can always switch to legacy one, which is an option, but the default is it's the same for all the tools now. And you see the list of the new default mouse assignments here. And on the Multiphase boundary conditions, there's a little change. Before you had to go to different tabs for different materials, but now it's all like a drop down. You can select, you have two phases if you're phase 1, phase 2, or mixture, and then you can impose the boundary conditions in a simpler, faster way. On the graphic side, there are some minor changes. For example, when you check the mesh, which is mostly used for showing the geometry, it does not show the edges. That was in most of the cases. You had to do it manually, but now it's the default, so you don't need to worry about it. It makes things a little faster. And in the transient simulations, you see when you run a transient case, it mostly saves a lot of parameters and shows it to you, but when you close and open the file, it would be gone. So usually you need to have a data set and save it so it's accessible later. Now there's an easier GUI for it. As you see here, if you select the surfaces here and then select the quantities you're interested in, and then you shift it to the data set, all the possible combinations which are available and can be saved would be saved inside the data set, which saves you a little time. The other product, which is inside the FPU package and has been gone through some updates, is the Chemkin. In the new Chemkin, it does allow the NASA 9 coefficient format for the thermodynamics variables that you put in it. It has the option to output tables in an easier way directly, but before you have to get a big output file and then post-process it. There is an update on the MFL or the model view library, which can save you some time. And the important thing is that it has been integrated with the ANSYS workbench, so you can do response surfaces, you can do parametric optimization, you can even create like a digital twin out of it, you can do all those functionalities that we have inside workbench. It's accessible for Tempkin as well. As you see here, in the previous versions, we had the NASA 7 coefficient fit for the thermodynamic properties, but now we can take the NASA 9 coefficient, which has 2 more coefficients, and it's a little more accurate. So it's compatible with it. For the outputs, when you go to the output controls, you can select any format you want and any parameters that you're interested in. So it would be saved and given to you directly at the end. The other thing is that, as I mentioned, the MFL or the fuel library has been updated. A lot has been added to it, a lot of hydrocarbons. It's a long list. I'm not able to read through all of it, but like isobutylene or alkene and etc. And the available models that we have for fuel components have been improved. For example, you see they have curves for ignition time, etc., and all the other properties which have been improved. And also some combustion kinetics have been improved and fine-tuned to get better agreement with the experimental data we have. As you know, for suit modeling also, we had some models inside that we again modified it based on the literature, and as you see, the new model is much closer to the experimental data, so you can use. As you know, the hydrocarbons and fuels that we are dealing with are quite complicated. For example, the gasoline that you have is almost 68 species, or if you have a little like isooctane, it's like 364, or the diesel could be from 171 to 445 species. If you want to do it manually and you want to get the data for all of those hydrocarbons and the properties and the mixture contribution and use it for your burner that uses diesel, it would be a lot of work. But the good thing is that when you buy the MFL, you'll be able to use all in one shot and it will save you a lot of time. Because these are quite complicated liquids with a lot of hydrocarbons in it, which is not that linear in the behavior. As I mentioned before, the Chemkin beta version is available inside the workbench. So you can bring it in, you can create response surface, you can create optimization, you can create even digital twin, all those things are available. There also has been some improvement in CFX and turbo tools. As you know, CFX is very popular, especially in turbo machinery design. I'll go through those very briefly as well. One thing is that now we have the GPU accelerated animations for transient like raw results. As you see, when you have the blade and you have the CFD on it, it has animation, and as you can even move it, it's live. It has like animated look, which is more visual and satisfactory. The other thing which was added is that, as you're familiar, GT is a very popular tool for system level study, and it has been extensively used in industry. And as CFX was very powerful in modeling turbo machinery, compressors, pumps, all those. So we made it possible to connect these two together so you can leverage the benefits of both at the same time. So you can set the system level study based on GT, and then you feed that into CFX, and they run at the same time, and it can tell you how the compressor or pump would behave. Or the other way around, if you do one change in pump, how the system level behavior would change. And one more thing is that when you want to create a response surface or the map for the turbomachinery, you can use the HPC parametric licenses and do it in one shot using that NVIDIA files, which is quite convenient. Another thing which has been added to CFX is the Gecko model. If you are a FLUENT user, I'm sure you have heard of this. It's a generalized K omega model, which is a K omega model, but it has fine-tunable coefficients. So based on the application, it tunes itself, or it can tune it manually. So you can get very good agreement between test data and what you see in your CFD model. This was already available in FLUENT from a couple of versions back, but now we include that in CFX as well, so we can leverage it. And one more thing is that the blade film cooling also has been added to CFX because it's a very popular tool in turbomachinery. So you can define the location of the pores or orifices inside your space claim model, and based on that, if you have the cooling because of those orifices, it can be modeled inside CFX. There were some other enhancements as well. For example, the CFD post supports the FLUENT CFF format, the files that we have probably seen with the .h5 extension. The partitioning that we had in CFX was quite old, so we had to improve it for faster results and shorter solve times. The solver up to 10% faster now, especially on the hex meshes because of the optimization we did on the numeric side. And also the solver memory is also a little optimized, so it has been reduced. So we need less memory when you run a complicated problem. These are most of the changes that we had in 2020 R2. There have been also some minor changes, I would say, in other tools such as iStack or so, but not that big. If you have any questions, I'll be more than happy to answer. Thank you all for listening.
There are two questions, Mason.
Okay. Can you read it, please?
Sure. The first one is any change in the recalculation of boundary condition where the outlet is inlet is eyelet for AC room or closed loop flow? It's under the question tab.
I'm trying to find where it is. Questions. One second. Sharing the cam. Okay. I can't really see the question tab here, but so in the boundary conditions, the ones you're asking, that's in FLUENT or CFX. I don't think there is a lot of change on that. Whatever was in 20 R1 and 20 R2, it's pretty much the same. So all the, as I mentioned, there were some updates in the aeroacoustic side that you don't need to calculate the coefficients, and it does it automatically, but on the inlet, outlet, or loop modeling, it's the same. It hasn't changed significantly or at all. The other question, please.
Yeah, the other question is, any improvement of plotting the fan or Porous equations properties as pressure flow? Any improvement? on plotting the fan or porous equations properties as pressure flow?
One thing is that, as I mentioned, inside CFX, you have, let me go back to the slide, I guess it doesn't hurt to go through that. Like this slide, we can use GPU accelerated animations for blades. Mostly that's in CFX, but in FLUENT, I don't think they have it. In general, CFX is very powerful in case of blades, a little more options or capability compared to FLUENT. FLUENT not update. I think it's whatever was regarding fan modeling inside the 2020 R1 and R2 are, I would say, identical, except this one, which is in CFX. And there was one more thing I think he was asking. Can you reread the question? In one part of yours I missed. Any other questions?
No, that was the last question.
Okay. If you guys have any other questions, you can send it to us at info@ozeninc.com, as showed in the last slide. Okay, so that's the email. You guys can email us if you had any more questions. I'll be more than happy to answer. And I think that'll be the end of it. If there are no more questions, that's it.
No more questions. Thank you, Mason.
Thank you, guys.